Have stabilized. So, folks, welcome to the July meeting of the RASC Ottawa Centre. Welcome to those who are joining us from other centres and visitors with us here this evening. We're recording this webinar for posterity. It will be available eventually at ottawa.rac.ca. Please use the Q&A box to ask a question to the speaker. There is a chat box, but we do not monitor that for questions. And just a reminder that your chat box comments can be seen by all. Raise hand is disabled. If you want to get our attention, please put something in the Q&A box. The RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and sky. So here's what we have on tonight. We've got the introduction, got one member in the news, got the Ottawa skies for July. We have Tony Peterson with some amazing solar imagery. Andrea was hoping to join us tonight, but she's lost her voice. So she will join us hopefully next month with her solar observing stuff. We have a quick break with AstroTrivia. Tim Cole is going to be talking about measuring a star's brightness. We have just a couple of observation reports this month, so we may finish a little bit earlier tonight. I apologize for that. And our monthly observation challenges will resume in August, and we'll finish up with some announcements. Welcome to our new members. So we have 10 new members in the last month, so welcome folks, and 46 new members in 2023. Members in the news. This is for Jeff Cohill. Let's go to the next screen here. And we're sorry to announce that Jeff Cohill has passed away in his 96th year. He was a member of the RASC, quite active a number of years ago before his health started to fail. And as it says in his obituary, he was a true rocket scientist. So we wish his family all the best at this difficult time. If you're interested in joining the RASC, a regular membership is $103. Family membership is $97.50 plus $16.90 for adult, $9.20 for youth. And for youth membership, $62.40. So what do you get for the membership? Locally, you get access to the Ted Bean Loan Library. We have a number of telescopes available for you to borrow. We have our own private observatory on the far side of the Mill of Kintail out near Almont. The Fred P. Lossing Observatory, and it's a very dark sky location, a really excellent location there. We will eventually get access to the Stan Mott Book Library, which is currently in the Canadian Aviation and Space Museum. When we resume our meetings there in the fall sometime, you'll be able to have access to that. But if you're interested in getting some beginning books in astronomy, please reach out to us. We do have some of the books at our homes and can get those to you. And then in terms of the national organization, you will receive a digital version of the journal. The Observer's Handbook, a hard copy book, is sent out in the December timeframe each year. And monthly, you'll get our amazing astronotes by our local editor, Gordon Webster. But one of the greatest benefits of being a member are those who are part of the society and the friendships that you make there. So these are just a snapshot of some of the folks who are involved here. So let's take a look at the Ottawa skies then for July. In terms of the moon phases, you missed it. July 3rd was a super moon. It's also known as the buck moon. And this is the first of 3 super moons. When we have a super moon, the moon is just a little bit bigger than normal from our perspective, but it's not a significant difference. And we have a new moon around the 17th or 18th. I didn't write down the date for that one. We had the Delta Aquarids meteor shower in July 29 and 30th. Unfortunately, that's right around the same time as we're moving back towards a full moon, so it may be difficult to see them. There's about 20 meteors per hour. Best viewing is after midnight and looking towards Aquarius, the constellation Aquarius. As you can see that the days are actually getting shorter as we move through. We just June 21st was the longest day of sunlight, and as we move through the month, it's getting darker earlier and earlier. So this is the rise and set times for the month. Mercury's rising and setting with the sun all month, so it's not visible. Venus is visible in the early evening and right through to the end of the month. Mars is visible in the evening and right to the end of the month as well. Jupiter is visible before sunrise, but you can see by the end of the month, it's going to be rising just after midnight. So as we move into August, we start to see Jupiter in the evening sky. Saturn is visible in the late evening and through the night. Again, as we move through the month, Saturn is rising earlier and earlier. So about 9:45 by the end of the month, you'll be able to, well, it'll be at the horizon. So about 25 minutes after that, you should be able to see Saturn. Uranus is visible before sunrise, and Neptune is visible in the late evening and through the night. And whoever lives in the middle of this shadow just had a telescope delivered. Isn't that true? I got some solar binoculars the other day, and we had 3 days of rain. So don't do that. No, just go ahead and wait for your for the skies to clear. Okay, let's move on then. Okay, so I'm going to turn it over to Tony Peterson. And let me just highlight you here. Tony, just give me a second here, spotlight you. There you go.
Okay, where we go. Hello again. This presentation has quite a few moving parts, so I turned it into a video once more. It runs for just under 16 minutes. I won't be using the live highlight window that you see there, so you might want to shut that off if you can. It'll be in the way. It's not apparent in the title, but you'll soon find out that this talk is all about my eternal quest for more resolution. So go ahead and run that video. Well, good evening. I would have been happy just to show a few images and videos of the sun and then disappear from your screen like this. But I was asked to also discuss the equipment I use a little, and as it turns out, I need to do this anyway so that I can account for some of the glaring imperfections in my work. I've moved away from using Registax as I find the convolved images provided by AutoStacker to be more flexible in post-processing than the wavelet sharpenings of Registax. Well, I imaged with my Lunt scope last summer exclusively in single stack mode as shown here. Now all hydrogen alpha setups have a narrow band interferometer filter consisting of two flat surfaces separated by some other medium. This scope has an interferometer gap filled with air, which can be pressurized to change its index of refraction and hence change the preferred wavelength of the transmitted light. This is accomplished by tightening a piston fitted with an O-ring as you see on top. This design works extremely well, and I'm very happy with the performance of this scope in that configuration. You can screw on a second interferometer, which is tuned by tilting the gap, and the combination of the two, which is called a double stack, will give you a significantly narrower band gap, which allows you to isolate features with better contrast. With a power made on, my camera yields a field of view as you see there in the bottom right, which is a good one for making mosaics in 4 shots with ample room for overlaps. Well, prior to preparing this talk, I never compared these bandwidths to the actual width of the hydrogen alpha peak that I'm sampling, and I thought I probably should. So I searched and I encountered this simple spectroscopic study that was a real eye-opener for me. First, the width at half maximum of the hydrogen alpha peak from the sun as we see it is around 2.5 angstroms. That's about 5 times as wide as a typical amateur instrument bandwidth. The peak is broadened because the photo emission takes place within very strong electromagnetic fields which affect energy levels everywhere. There's a Doppler effect from the thermal motions of the emitting atoms, and the emitted photons can interact with the electrons as they pass through the rest of the sun's atmosphere. Well, hopefully one's instrument is able to scan across this range. I'm not going to go much into tuning subtleties today, except to say for now that I spend nearly all of my time on the blue side. What really got my attention in this figure was the small absorption peaks from high Cirrus and the fact that the hydrogen alpha peak on the disk is a huge absorption peak, which is to say that nearly everything one images in hydrogen alpha on the disk is seen as a shadow against the thermal emission of the photosphere. Of course, flaring at all wavelengths can be brighter than this background lighting, so processing solar images can force you to make compromises. However, it gives a good rationale for viewing solar disks inverted, which is something I had always hoped for before now. I find the fact that there is a haze-related absorption peak right on top of HA very disturbing. If you are tuned on top of or even near that absorption, you're likely to get very uneven results in both time and space. And I think I have examples to show you. So here's some recent imagery with the single stack LUNT. As you see, on May 25th, there were a number of unstable active regions, as well as an outside spot labeled 3310. I decided to run a time lapse because the active region 3311 in the middle of that strip above the equator was reported to be prone to flaring that day. But instead, active region 3312 did a neat thing. So this image was obtained at the end of a time lapse that I took. Here's what happened. The action starts when a high arcing magnetic flux loop flares with some entrained plasma, and then suddenly some smaller arcs beneath it resort their connections in some way, resulting in strong heating. They end up in two closely spaced parallel flux lines, which looks to me like an awfully unstable configuration. Despite the obvious energy released here, this event didn't even make it to the daily list of flare events of Class C or above. So what about double stacking on the LUNT? Well, when you tune the tilt tuner on the LUNT, this is the result, and I processed it a little to show the disk features better. As you can see, the tuning is very uneven, and the best position is probably 2 steps back from maximum tuning, where the unevenness is at least fairly symmetrical. But there's another problem that you see when you process as you might for the chromosphere. So you brighten things up. The tilt tuner generates a reflection, which is most obvious when it's half off, as you can see on the top line. Fortunately, this reflection is well out of sight for the setting that gives the best disk image. This reflection is barely visible in visual mode, and the double stack LUNT is a good observational instrument, but it's difficult to use for imaging. So here's a 4-piece mosaic from May 30th. It was captured in single stack mode. The images are really quite homogeneous and they're very easy to patch together. The single stack image is significantly brighter than the double stacked one, so you can run at a lower gain and faster shutter speed, which is always a big advantage when you're doing solar imaging. Well, active region 3319 was of some interest as it flared almost continuously the whole time it was crossing the sun. And on May 30th, it was the only region to flare at level C or above, and it really wouldn't quit. This could have been processed a little better, but no enhancement would have made it comparable to this image, which was captured the following day. So this was captured using the same camera with a Daystar Quark chromosphere filter dangling from a TeleVue 85mm refractor. Now, this has a bandwidth that is likely a little smaller than the double stack LUNT. It's potentially as narrow as 0.25 angstroms, according to Daystar. With the additional optical resolution of an 85mm f7 telescope, the Quark is equivalent to a 4.3 times power mate. You obviously get a much nicer image. So here is that TeleVue refractor hard at work. There's a UV IR filter screwed inside one of the extensions, and that provides all of the pre-filter energy rejection that's needed for such a small scope. I also tried earlier on an 82mm red filter screwed into the cell in front of the objective. I saw no difference in the performance with those two, so I'm keeping to the infrared filter because it's better protected inside the optical train. There's a tilt plate in front of the camera. I had to put that there as I did get intense Newton's rings when I first started using this setup. So this page is from Astronomy Tools. I plugged in the numbers for the scope and the camera, and as you can see, The ASI 174 camera is a very good match to the TeleVue 85 plus the Quark. It's just under oversampled. So this is what you see when a Quark tunes up. At startup, the image is much like that of a white light solar filter. It uses a 5-volt USB power source to heat the medium between the interferometer surfaces, which changes its index of refraction, and this takes about 10 minutes from startup. Here I'm tuning to a middle position, which is at clock position on the control dial of 12. You can see that at no time after the interferometer kicks in do I get an even response across the field of view. I should mention that a response like this is within the range that Daystar says we should expect. They point out that you can get a much better result by picking up one of their $15,000 research grade filters, and they probably have a point. I suspect that one could have been luckier than I was in the quality of the Quark though. And now with a better focus, tuning from 12 to the blue side of the peak at position 9, which is where I usually work. The evenness of the response improves a little, and the left 2/3 of the field of view looks salvageable. So on May 31st, I tried getting a flat by pointing the scope at an area on the sun that was free of active regions and filaments, and as far from the limb as possible, and defocusing. Well, you can't always find a spot like that, but there was one to be had this day. The sky was pretty good for Ottawa, but there was a bit of white haze in the sky. The results are pretty good, but you can see a small amount of large-scale unevenness in the brightness, which I could not entirely eliminate. I used Photoshop to assemble the pieces after I placed them myself, and it does a fine job of brightening and darkening on gradients to get pieces to match along the edges, which is why you can't see any actual seams, but there are clearly domains that are anomalously light or dark. Now, a couple of neat things happened on the sun on May 31st. That active region 3311 that was supposed to be flaring several days ago finally did so as I was looking at it, just as it was disappearing down the descending limb. I noticed this neat feature, and so after I captured this in a stacked image, I took a quick time-lapse video. I've washed this through image stabilization, but I think I need to find better software to do it. Anyway, this begins with a large volume of plasma being entrained upward along a magnetic flux arc. It stops and then it falls backward. And maybe when it does so, it compresses, heats up, and indulges in a bit more flaring at the base. Then there's another burst of plasma entrainment happening on the other side, the opposite side of the active region, and it's probably just on the opposite side of the same flux loop. So that all happened in this location. On the other side of the sun, I captured the disintegration of a plasma-rich flux loop. Now, the top of this loop is much cooler than the base, and so it's imaged largely from its absorption shadow, which gets more intense the higher it rises. Although it is possible to pick up the top of the loop as an emission when it rises above the limb if you process it aggressively enough. So it looks like it simply decayed, losing its top in a small coronal mass emission. June 4th was another busy day, but it was distinctly hazy. Now here's a quick look at a couple of photogenic active regions. Note that the large sunspot is beginning to disintegrate. It's developing so-called light bridges, which are bright lanes developing between the pieces. And I imaged something that I thought was unusual. There's an arcuate inward dipping curtain of what appear to be small on-echelon connection loops that are surrounding that bright plage region through at least 180 degrees. You can see there's a crest of relatively cool plasma along the top, and I presume that this feature would develop into a filament. But I checked up on it a couple and 4 days into the future, and it turned up no filament at all. Now, if you look at the potential field lines, you can see that the plage area is an unconnected unipolar region, with field lines streaming right up into the corona, and the sunspot, which looks normal in the image, is wildly bipolar. So my guess is that the curtain is related to the plage area and has nothing to do with the spot, but I don't believe I've ever encountered a description of this sort of feature, and I don't really know what it is. So here's my flat of June 4th, and it's gratifying to see it's virtually identical to that of May 31st, so I'm doing something right. I attempted another mosaic that day, but it's obvious that something wasn't right. And in this case, you can even make out the seams between the pieces. There was a lot of gradation in the brightness across individual images. So, one more try, June 22nd. And on this day, conditions were very good in the morning. I had good transparency, no haziness that I noticed. It's subtle, but this flat seems to have less contrast than the one on May 31st. Bingo! It's hard not to conclude that the quality of these mosaics is a strong function of the quality of the transparency that I'm seeing the sun through. Okay, so let's look at a couple of colorized versions. Harder to keep the high contrast and the visual detail in these, but they are a little more pleasing to the eye. I should mention that this background in the atmosphere is probably just due to scattering of light in the scope. Its apparent structure is actually imposed from the flat. This is a terrific sigmoidal filament, which also shows some chirality in its fine structure. Don't have time to talk about this interesting kind of thing today. So I learned some lessons by doing these mosaics. The most important thing I learned is I can do it. It takes a lot of pieces and a lot of work, but I can make good, high quality, high resolution mosaics. Second lesson is I can't do it all the time. Gotta have good sky conditions. The third thing I learned about solar observing is that taking time lapses is a lot like birding. You point your camera at a likely perch and you hope that something happens. Thanks for watching. Okay, am I on again?
Yeah, you're on. Thank you, Tony. So I'm just
Okay,
going to see if there's any questions. No questions yet.
No questions yet. Well, we're just waiting for another minute. I'll just say it's too bad Zoom can't handle the animations. I guarantee they are much smoother than they appeared there. So you can see the video on my own YouTube channel if you want to see it nice and smooth and in high resolution.
Okay. So Tony, if you could, when I think we've got a copy of the video, but if you can email us with your YouTube links, we'll put it in the Astronotes. How's that?
Yep. Okay. Do that. Yep.
Okay. That's great. So a bunch of thank yous. Any questions for Tony, folks? No, well, I really appreciate your presentation, and we'll have a follow-up with Andrea, hopefully next month. She will add to what Tony has presented with us today.
Yeah, it's too bad the imagery she had was very complimentary to this.
Yeah, absolutely. Okay, well, thank you very much, Tony. And if you have some questions that you think about after the fact, feel free to post them. We will have time to answer them if you want to sort of hang on the webinar for a little bit there, Tony. And maybe after the break, if there's still some questions, we will attempt to answer them. Great, Thank you.
I went around looking for a marvelous night sky shot. This one from the Atacama really gets at the crux of it. One of the big things you can get with a beautiful starry sky is a huge range from brilliant colored beacons to tiny little dots that you're barely even sure are there. As with a lot of things in astronomy, you're going to discover that people have been trying to assess things like brightness for a very long time. And the magnitude system we're using now has ancient roots and has mutated considerably since its foundation. And as with many things in astronomy, it's also a bit wonky. Come on, be kind here. This is a chart showing how the stellar magnitude system works. For the folks that have been doing this forever, of course, this is just old hat, but for newcomers, this can be a little bit confusing. Up here in the upper right, the sun is at a massive -27 magnitude. And as we move over to the right, we end up coming to Vega, which we'll come to a little later, with a magnitude of 0. And if that hasn't twigged on you just yet, we'll go down here to this dim star symbol, which is showing the limit that you can see with your Mark I eyeball in a nice dark sky at a magnitude of +6. You can use binoculars and telescopes to get down, but to higher numbers. If you're using one of the Keck telescopes, you can get down to about -27. The record for Hubble was -31, +31. And the James Webb telescope can go fainter, but it's in infrared, so that doesn't exactly count as a visual magnitude. Now, it seems a little strange that you'd have numbers that get numerically bigger and have a star that's dimmer, and you might wonder, how did we come up with such a counterintuitive system? And of course, the answer is because it's ancient, and we stuck with it, which you'll find a lot of in astronomy. The system we're using now is very loosely related to the system credited to Hipparchus of Nicaea, somewhere around 150 BCE. Now, it's credited to him. No doubt it had been around for a long time before he wrote about it. And it probably reflects standard procedures for astronomers of the day. What they did in those days was assessed brightnesses and in a very qualitative way. Sorry, not quantitative, very qualitative way. Just this one's bright, this one's not so bright, and put them in categories, which I'm showing here as bins. So the very brightest star in the sky, very brightest stars, dump them in the first magnitude bin. They're noticeably not quite as bright, dump them in the second bin. The ones that you can just barely make out even on the faintest, darkest nights, toss it in the 6th magnitude bin. So remember that even though these are numbers, I've actually read some references that suggest these were marked with Greek letters, but I'm not terribly certain about that. But the thing is to consider that as a very general statement, a bit like saying a Rolls Royce is a first-rate car, and the beaten up junker that you just sold for $52 is a 6th-rate jalopy. And that's how to consider these magnitude systems. If we move a few centuries ahead, give me a sec here. Here we go. Move a few centuries ahead, and I love this here. This guy Ptolemy. I'm sure he didn't look like this at all, but somebody painting in the Middle Ages, that's what you get. Much of what we know about astronomy from those years comes from Ptolemy of Alexandria's book, A Mathematical Compilation, which sounds like a real page turner, I know. Written in the 2nd century of the Common Era, Arabic scholars began to refer to Ptolemy's work as the greatest compilation. And when the book made its way into Europe, it was widely known by a Latin transliteration of the Arabic word for greatest, the Almagest. which you've probably heard at various times. 2 chapters of the Almagest comprise a star catalog that includes assessments of stellar magnitudes. And the magnitude notations in this case include notations major and minor. So he subdivided the 6 bins a little more tightly than that. And again, this probably reflects what common practice was for astronomers at the day. Now, as near as you can see, this system didn't change very much for quite a while. And since European scholars tended to regard Ptolemy with something approaching reverence, it's not surprising that it didn't really change much. And there really wasn't much point. I mean, you're looking up at the sky and saying, yep, that one's pretty bright. That one's not so bright. And then that's about as much as you could even do at the time. It didn't make much sense to do anything more. Moving ahead, you probably recognize this guy. Once you started looking with the telescope, you quickly discovered that there are plenty of stars that are much dimmer than 6 magnitude. By definition, since you couldn't see them with your naked eye, they had to not be in the 6 magnitude bin. But I found it quite frustrating trying to pin down details much after Galileo. I'm sure that astronomers of his day and for quite a while afterwards would have made some efforts to record their assessments of how bright the stars were, but I can't really find very much data on it. And now it could be that, I'm simply don't have access to good historical records. I'm working with textbooks and what I can track down through the internet. But I suspect part of it is it's just sort of glossed in. And we didn't really have technology to do a whole heck of a lot more with it anyway. But along comes, surprisingly enough, or not surprisingly, I'm being sarcastic here, William Herschel. You probably recognize the name. And if you're like me, regularly confuse him with his son, John Herschel. A massive figure in astronomy. Unlike Carolyn, who doesn't tend to get mentioned very much. Recording stopped. Well, anyway, shall I continue? Okay, I guess I will. Something I said? Oh, well, never mind. Herschel began getting interested in measuring brightnesses of stars in a rigorous way. And by around 1800, he'd made a very good compilation of about 3,000 stars, making very good estimates of brightness with respect to nearby stars. It appears that a number of astronomers had done this before Herschel, but what really distinguished his work was that this was the kind of work you'd expect of Herschel. Very well done, very well documented, probably because Carolyn did the documentation. And extremely rigorous in how he presented the work. Now, there are a lot of astronomers doing a lot of major work around this period, and it's hard to pick out just 1 or 2 of them. So I'll focus on Friedrich Argelander, best known for a massive star catalog, and I'm probably going to butcher the pronunciation here, so have some patience. The Bonner Durchmusterung star catalog, completed in 1862. You probably recognize this more by the initials BD, which you'll find in a lot of star designations, BD and a string of numbers afterwards representing the coordinates. Now, Argelander and his assistants really made a change here in how. You're okay here, there, Chris? Okay. The big difference here was that Argelander formally extended the magnitude system to telescopic stars. So here you have distinct references to numbers numerically greater than 6. And he also introduced decimal subdivisions instead of notes like major and minor. So these would be the first steps in establishing a numerical value instead of a qualitative reference. Now, they were still at this point being done by skilled observers just using their own subjective impressions of brightness. But even so, these were considered some of the finest magnitude figures available well into the late 1800s. Now, we move from there to William Herschel's son, Sir John Herschel, another magnificent figure in astronomy. And Sir John Herschel had started working with what were at the time the very new technology of photometers. And by 1830, he'd amassed enough data that he was able to make a statement that he felt he could back up, that the difference between a 6th magnitude star and a 1st magnitude star was a relative difference of about 100. In other words, a 6th magnitude star was 100 times fainter than a 1st magnitude star. And this wasn't a question of the subjective, 1st magnitude bright star, 6th magnitude dim star. He was trying to make estimates here of the luminous intensity and established that there was a significant relationship. Now, if you take Herschel's comment at face value, you might expect something like this: a linear relationship. You've got unity brightness here. Don't forget, all this stuff had to be done by comparisons rather than actually measuring the light per se. And then down here at 6th magnitude, 1/100th of that intensity. Now, astronomers in the mid-1800s realized that this relationship couldn't possibly be just a simple straight line. But they also didn't know what it could be. And that may seem a little odd to us, but we have the advantage of retrospection and a lot of other work that had gone on at the same time. You can get a sense of just how much this was new and groundbreaking work from a citation that I'd read, a comment that I'd read without any citation to a reference from Argelander. He raised the possibility of a logarithmic relationship between intensity and magnitude as an arbitrary suggestion. So you'll read some references that suggest that it was known that the eye responded in a logarithmic way. And it turns out that actually the work involved for that from people like Fechner and Weber, which I hadn't intended to get into, but here I am. That stuff was actually published much later than Argelander's comments, and later than the stuff that I'll get into in just another slide or two. What we know now, in fact, is that the eye's response is actually follows a power function rather than even a logarithm, and the differences in the curves are actually fairly slight. Now, I want to take a bit of a side trip here. Since we've mentioned measuring light, it's not a bad idea to take a look at photometers. This is another area that's remarkably hard to track down. There are plenty of descriptions, but not a lot of really good solid descriptions. Now, as it turns out, in the Old Dominion Observatory, the one we're busily trying to preserve down on Carling Avenue, they had in their observatory buildings a wedge photometer, which is now in the Science and Technology Museum of the Ingenium Corporation's collection. And what this did was allowed an observer to use this little hand crank mechanism to move a wedge of optical glass that had been tinted, so that as you moved the wedge through, you'd attenuate the light to a different factor. And you would compare, the operator would then compare a reference light on one side and the star being tested on the other, and move the contraption until the dimmer, the brighter light was dimmed down to match the dimmer one. And the nice part with this particular one, as you can see here, it had a stylus and a moving chart paper, and that seems to be a kind of a nice feature for photometers at the time. The reference varied tremendously. It could be a candle, could be a gas burner. Of course, back in the 1800s, you wouldn't have had anything like reliable lights. And, there were attempts to come up with standard candles made from various combinations of whale wax and oil and such like. The other possibility for a reference might be a reference star. The big thing to remember here, though, is that we're still using an operator's eye to estimate the degree to which whatever was working in the photometer dim the incoming light. So it's still, the only detector around is still an eyeball. All these things did was mechanized it and allowed you to do it in a repeatable way. Moving ahead, here's another example of another type of photometer. This is a meridian photometer, and it's similar to the ones that the Harvard College Observatory used to produce a groundbreaking photometric survey published in 1884, which was long regarded as one of the great standards of photometry well into the 20th century, from what I can gather. And in this system, you have two telescopes, which are linked through a system of prisms and mirrors that allow you to directly compare one star to another. And you would then use polarizers to adjust the brightness of the stars until they matched. And again, it's the same problem. You are using a skilled observer to decide how well the match is. But one advantage with this, instead of simply an observer looking at the sky and saying, yeah, I guess that's 6.4, I guess that's 5.2, you're looking at a mechanical widget so that another observer could at least come and look over the shoulder and said, yeah, I think you've got it matched well, or no, I don't think you have it matched well. At least it's an attempt to provide some kind of repeatability. Even so, it was established at the time that if you were going to do any kind of work with magnitudes and magnitudes of references, you wanted to get data from one observatory, if possible from one observer, and if really possible, done in one observing run, which might be several nights, but with the same equipment setup and the same configuration for telescopes and reference lights and all that good stuff. And of course, you know, with the length of time that it takes to get all this material, that's not always practical. Now, no matter what kind of photometer you use, you're going to discover that the relationship between relative intensity and magnitude is something like this. Now, I've actually fudged this a bit. I've produced this graph from data reported in a 1962 article in the RASC journal by Michael Burt Gaffney, and which he's describing some of the history of this, of the photometric efforts, and actually comparing it to some of the work being done in psychometry to get an idea of how people perceive things. And this is very roughly what you will measure. It looks like a nice, simple logarithmic curve, but it really isn't. This is a patchwork quilt of data points and curves to interpolate between the data points. And it is numerically something of a mess. Not a problem today, but back then it was. Now, what I have here is a yellow curve that is just a nice, simple, easy to compute logarithmic curve. Excuse me. Now you can see there's a bit of deviation between this and the blue curve, but it's fairly close. Now, fairly close doesn't seem very good to us today, but it's easy to miss the significance back in the 1800s, in the late 1800s, and even into the early 1900s. When a job description of computer, you know, referred to somebody who actually did hand calculations instead of a device, computational efficiency made a huge difference. If you had to do hundreds and hundreds of repetitive calculations, a function that's good enough becomes a very valuable thing to have. So what I wanted to do now is take a look and see where that curve came from. And at this point in the story, we introduce an astronomer that very few people have run into before, and it's a chap named Norman Pogson. In fact, we'll see him show up a little bit later in a chat about helium, but Pogson is one of the old British astronomers in the Raj era, observing mostly in India. And he mostly seemed to have done what I would call workhorse astronomy. He filled data books. He did a lot of the stuff that you depend on to get more important things done. And so, you know, he was one of these people, not a lot of fame, but you don't get much done without him. He had done some photometric measurements that seemed to be really in vogue in the day, and also looked heavily at the work done by other people like, you know, Arglander and the Herschels, as we saw. And he concluded himself that a logarithmic relationship was probably a good, reasonable relationship to work with. And his next trick, his next problem was to come up with a relationship that was going to be workable. So in 1856, he came up with this equation. Now, yeah, I know for some of us who haven't cracked a math textbook since high school are going to look at this and start to gasp a little bit, but it's actually a pretty straightforward equation. Two magnitudes. Remember, we always at this point, and even now, we're looking at not so much absolute magnitudes, which actually that's another overloaded term for another day, but we're always looking at differences in magnitudes between a reference and the star you're measuring. And this happens to be this magic number and the logarithm of two intensities, the ratio of two intensities. Now, this is a fairly easy calculation to do. You can do it with standard tables. It's an easy calculation to do by hand. It's very easy to plot. You can use standard curves. It's a very easy thing for a human computer to handle. If necessary, you can apply correction factors very easily to this. So it's a nice fact. It's a nice function. And this is pretty much where it ends in most of the textbooks. But I was kind of curious, how did he come up with this? Which you can find in a few other textbooks, but you have to find dig a little deeper. Pogson's trick was to actually just pay attention in noticing, first off, that with the traditional, the classical magnitude system, you have 6 magnitudes, which gives you 5 intervals. And Herschel the Younger had been able to verify that there was a 100-to-1 relationship between this faint star, the luminosity of a 6 magnitude star, and the luminosity of a 1st magnitude star. So since you had 5 intervals and a logarithmic curve, so you'd be multiplying the intensity of a dim star by a factor and then multiplying again by a factor and so on. What Pogson wanted was a single simple equation, and the number he picked was the 5th root of 100. What number, when you multiply it over and over again, would give you 100? And that happens to come to within 3 decimal places to 2.512. And in fact, you'll find a lot of literature that simply uses this as 2.5, which again seems kind of terrible, but it actually turned out to be quite good enough in the day. So this is where Pogson's ratio comes from. It's the 5th root. It's the 5th root of 100. And this comes to Pogson's formula, which again, you'll find in all the standard textbooks. And this is how you relate the intensities. Now, the thing to remember here, though, is you don't actually need to know what the intensity of the light is in terms of measurements like lux or watts per square meter, or as a friend of mine is always horrified with, Janskis. All you need is the ratio, the relative intensities as a unitless number, and that you can get with regular photometers with considerable ease, actually. Well, I shouldn't say ease, with considerable repeatability. These things would have actually been bears to use and would require tremendous skill and practice to use them well. But nonetheless, I mean, you could get them and use them. And this equation, even though it wasn't going to work rigorously for every star at every magnitude, worked fairly well. And Pogson's ratio came fairly close to other numbers that other astronomers like the Herschels and Argelander and pick a name from astronomy, Struve and Argelander and Groombridge and all the other ones that you see in the catalogs and don't really know who they are. The numbers came close to what they were always finding for different groups of stars. So he knew Pogson knew this was a compromise, but he was convinced that this was a fairly good one and proposed it to the Royal Society. And it was adopted as a good, useful feature, a good, useful formula for general purpose use throughout astronomy. And to do any better, you've got to do an awful lot more work. And you actually need better computational equipment than they had available. Nowadays, of course, it's trivial. I mean, you can do it in your smartphone, but back in the day, it wasn't. What his system did was it linked this classical system of the 6 bins to the modern system, which is a nice continuous reference, a nice continuous scale from open-ended to open-ended. And you might wonder, like, why bother? I mean, okay, if we've come to this new system, why come up with such a silly backwards type system that's kind of clunky? And I don't know. What can you say? I mean, it's tradition. We do that a lot in astronomy. And it's nice to be able to go back to some of the older stuff and be able to make use of it, so that you can keep using the work of, people like Argelander or, Hevelius or whoever, and at least maintain it. And you can also go outside and gauge a star's magnitude with the Mark I eyeball and compare it against a chart. So does it really make a lot of sense? Perhaps not, but it is tradition. And, you'll find we have a lot of that in all our sciences. Enter a big shift in photometry. And this one, it turns out to be remarkably obscure. A telegraph engineer by the name of Willoughby Smith, working for the Gutta-Percha company, installing telegraph cables, discovered quite by fluke, as near as I can tell, that selenium changed its resistance. A selenium rod would change its resistance when exposed to bright light. He was trying to put a test load on some telegraphic wires and picked selenium as an example of a material that would behave in a way he wanted, but discovered that his measurements were all over the place, and quickly discovered that was the amount of light coming into his workshop that made the difference. And in 1873, he published an article in Nature magazine describing the change in resistance in a selenium rod. And as near as I can tell, that seems to be where Smith's contribution to this seems to have just disappeared into the ground. And you can hardly find this any written down in too many places. But even so, this one contribution just completely overhauled photometry. 1907, we have Joel Stebbin at the University of Illinois Observatory doing photometric work. And he decided to switch from a standard visual photometer to try this selenium system that had been fiddled around with in labs, and hooked it up to the 12-inch telescope at the observatory, and was able to measure directly the difference in brightness from one side to the other of the moon's terminator in February of 1904. First astronomical use of the electric photometer. Now, at the time, I mean, if you can imagine the moon, it's not exactly an easy, a very dim target, but he and another fellow, F.C. Brown, who I can find virtually nothing about. If anybody's got background on this fellow, I'd love to know about it. Were able to improve the performance of this selenium monstrosity hanging on a telescope, to the point where they were able to measure the light curve of Algol just 3 years later. You get an idea of the bulk of these things. This selenium box here had to be connected to a galvanometer, this thing here that looks a little bit like an ocarina, and a whole bank of batteries and rheostats and such like in a room below the telescope. And here they're actually plotting, according to the blurb from the University of Illinois, plotting the light curve of Algol. Now, that was a big change, but it was going to take a long time before you could actually get really good performance. These were very finicky devices, required a lot of care, a lot of upkeep. They were fragile. You had to get the voltages applied to them just right. So these were not easily used devices. And in fact, they were still using visual photometers for quite a while after that. Now, I've mentioned a few times here that you were going to always use a reference star. We're always looking at differences in magnitude. So what's the reference? numerous photometric surveys, including the Great Harvard Observatory photometric survey, used Polaris as a reference star, largely because it was, you could put a telescope right on it and you wouldn't have to worry about it moving. You didn't need a lot of elaborate control systems to work it. You were limited to the stars. In fact, Harvard did what they called the circumpolar survey of stars, but it turns out that Polaris is a terrible photometric reference. It's significantly variable and not even variable on a good basis. The variability rate is awkward, so it's not the best. So by the late 19th century, Vega, and for a number of reasons, turned out to be a nice, attractive reference. It's close enough that you can measure it. You can measure its distance with trigonometric methods, so that's nice. So you're not having to deal with differences in inverse square law effects. And as far as anyone could tell until the 1930s, it seemed to be not a variable star, and very easy to find, very accessible to every observatory in the Northern Hemisphere. So it was accepted as a photometric reference. And in fact, for a long time, its magnitude was officially defined as 0 with no uncertainty. I don't know if that's changed or not. I think the IAU may have changed that, but I'll have to check on that. Now, by the 1950s, photometrics had improved to the extent that you're using electric photometers all over the place, and Vega simply became one of many reference stars. And now you're even looking at synthetic references. So it's still valuable, it's still useful, it's still an interesting star, but it's no longer the gold standard for photometric reference. One of the interesting things with Vega, though, is it's arguably one of the most studied stars in astronomy. In fact, having the distinction of being the star for which the very first photograph was made on the night of July 16th, 17th in 1850. And here you've got a scan of the daguerreotype of Vega. It was also the first star for which anybody produced a spectrum, an absorption spectrum. At this point now, we're at a stage where anybody can do photometry. And I just tossed in here just a set of curves for a standard set of Botter Planetarium Bessel filters, which you can buy for, I think, at an inch, I think at 1.25 inches, I think it's something like €1,000, which to my mind is awfully expensive. But, if you're really into it, I suppose it's one of those, I call it a doghouse price. You can probably find the money, but you are going to be living in a doghouse. And what this allows you to do is a very wide range of photometric work, even from your backyard. And of course, this system is just one of the beginning systems. And when you look into it, you'll find a dozen different photometric systems just listed on one reference book, and dozens of filters. So as long as you're willing to use software and take a black box approach, you can work out the photometry yourself. You'll find, though, that this is a frustrating field if you want to dig deeply into it. Photometry and radiometry, it's an area that's a little tricky to get into. I've been struggling with it for a few years now. There's a bewildering array of variables and names that are very similar but not the same, and are used differently in different fields. So there's some traps for the unwary. But it is an interesting field to peek and poke around with. Of course, you can always just go outside, look up at the sky, use your Mark 1 eyeball, and see how well you did against the night chart. So there's always that. I could have babbled on an awful lot longer. I had decided I would cut it off at this point. And if there's anybody who's still awake, if you got any questions, by all means, toss them my way. And thanks for putting up with another one of my little serial obsessions.
Okay, thank you very much, Tim. Do we have any questions for him? I don't see any in the queue yet, but I apologize for the interruptions with the recording on, recording off. It wasn't you, Tim. It was Chris was having internet problems, so he kept dropping out and back in again. So
I think it's they just don't like Canadians.
something like that. So we're going to resume with the observation reports then. Again, if you do have any questions that come up after the fact, please type them in. Thank you from Brian McCullough to Tim. So first up is Richard Taylor. Hang on a second, Richard. I'm going to spotlight you so everybody doesn't watch Tim for the rest of the evening. There we go.
Okay. This is a view of the recent conjunction of the Moon and Venus and Mars. I just went out one evening to take a look at Venus, and the Moon was right there close to it. So it was a great photo opportunity. I started snapping away all different kinds of pictures. And it wasn't until the following morning that a friend of mine in Toronto pointed out that Mars was in the same field of view. So I went back looking through my photos and found that I did capture it in one or two of the pictures. The next one is a labeled version. So Venus, of course, is extremely bright right now. It's probably visible at the moment. And Mars is a lot fainter, so it's not easy to see with the naked eye. You have to wait until it gets a little bit darker, which doesn't happen until quite late these days. Next one. Now this is a close-up using my 8-inch Schmidt-Cassegrain telescope. I've been taking a sequence of pictures of Venus throughout this recent apparition. And you can see how the phase of Venus is changing, gradually becoming more of a crescent as Venus comes around between us and the sun. And also it's getting closer to us, so the apparent size is changing. All of these pictures were taken with the same settings on the camera and the telescope, so they do show the relative apparent size of Venus changing. I'm hoping to get a couple more pictures before it comes right between us and the sun, but I have a difficulty with lots of trees in the west. Next one. Okay, my most recent astrophotography project has been to try and start using the 14-inch Meade telescope, the Paul Commission telescope at FLO. Paul Collinger just recently conducted a training session for myself and 2 others, so we can start using it. And he's managed to solve the initial pointing problems that he'd been struggling with for almost a year now. And basically the solution is turn off the GPS. We know exactly where FLO is. And we were just using the GPS for the time signal, and it was not coming out correctly because of a battery problem. So if we turn off the GPS, enter the time manually from some other source, then we can get the pointing to work out fairly well. This is just a single picture of the moon showing what it does with my Canon M100 camera. And the next picture is sort of a 3-panel mosaic of the moon taken the same night. Since that time, I went out one more time this week and got a picture of M27, the dumbbell nebula. So maybe I'll show that next time, or let's see if I can do some more. Anyway, things are working. More training will be available later on in the summer. So I encourage people to start using this lovely telescope. Thank you.
Okay, thank you, Richard. And I'm going to turn it over to Bob.
Yeah, hello. This galaxy was suggested to me by Mike Worths. He was fascinated by the narrow and distinct dust lanes and wondered if they would show up in a photo. It is about 60 million light years away, and it is about a 10th magnitude galaxy. It shows up easily when imaged. It is part of the Virgo 2 group. And the dust lanes are really unusual, for sure. Next image, please. The spindle galaxy. This is one of Oscar's challenge objects. To me, the most interesting thing about this galaxy is that it may not be M102 as suggested. Apparently, Messier did not give coordinates to this observation, and this galaxy is 14th magnitude. Thanks to Tim, we all completely understand that now, which is probably dimmer than Messier's equipment would allow him to see. Interesting center dust lane. Next image, please. Another of Oscar's challenge objects. This galaxy is about 29 million light years distant and has an apparent magnitude of 10. It should be easy to see in a telescope. My first image of M108 was taken in the year 2009. So starting in 2009 and ending in 2023, I have imaged this galaxy for 8 nights. I thought it would be fun to combine all the images from these sessions into one image. It was not as easy as I thought it would be, but here is the result. It does show a lot of detail. So basically, this is an image of the decades. Next image, please. This summer, I pointed my telescope at the Whirlpool Galaxy for 8 evenings. These sessions did not last the entire evening, but were just fitted in between other targets while I was waiting for clouds to clear or targets to rise. The moon and forest fire smoke did not help my data collection. But this is one of my favorite targets, and I cannot resist pointing my telescope at the handle of the Big Dipper where this galaxy pair resides. After my success with M108 imaging over the decades, I decided to look at my career data for M51. It turns out I have imaged it over 58 times and amassed 2,273 individual frames. Combining this many images is a daunting task, which I finally completed this morning. Thus, you will not see the image tonight, but maybe next month. Thank you.
Thank you very much, Bob. So let me just hang on a second here. There we go. So the Fred Lossing Observatory is available for use. And Chris, I think there's another overlay for this, or maybe it's on the next slide. There we go. The Flow Star Parties, these are for members only. Our next one is July the 15th, weather permitting, smoke permitting, and so on. So hopefully you will, if you're on our distribution list, you'll be getting a welcome, or sorry, an email confirming whether or not this is a go.
Dave, I hope these are a little more successful. When you see the previous ones crossed out, it doesn't mean that they're in the past. It means that they didn't happen thanks to the clouds. So we're
thanks to the clouds and smoke. Yeah. So we're due one. Absolutely.
No one buy new equipment.
No more new equipment between now and July 15th. Okay. Not for the next week or so. Okay. We have a public star party on Friday, July the 21st, with the rain date the 22nd. We meet at the parking lot of the Carp branch of the Ottawa Public Library, right next door to the Diefenbunker. We have the ability to turn off the parking lot lights. And what we do is we set up the telescopes in the observing site, as you can see on this image here. Cars are parked above that. And you'll be surprised, we may have 30, 40 telescopes and 300 people out. So it's a great public outreach. Hopefully the weather cooperates. And as you can see, we have been very successful so far this year. Anyways, let's hope we get good weather. Here are some of the folks that run our club. So Rick Scholes is the director of our Fred Lossing Observatory. Estelle looks after our book library. Peter Shute looks after our telescope loan library. The Coffee and Conversation, until we move back into the Canadian Aviation and Space Museum, We don't need somebody, but if it's something that might interest you, please reach out to us. So we're ready to go once we're back in there. And the RASC membership information is well kept by Art Fraser. We had around 50 people tonight, so thank you to all the presenters, and thank you to RASC National for the use of their Zoom account. I'd love if you folks have any comments or ideas. I'm looking for speakers. I'm doing this off the top of my head. I believe October is where I'm short on some speakers. So if you know somebody who might want to speak to us, or you've got something that's a burning interest of yours in astronomy, please reach out to us, and we'd be happy to work with you on putting together a presentation. So our next meeting is delayed by a week because of the August long weekend, and I'm going to be handing over the reins of meeting chair for that meeting to somebody very familiar to you. Oscar is going to be looking after the meeting. I'm traveling at that time of the month, and we have a number of interesting presentations coming up for that meeting as well. Again, any ideas, meeting chair at ottawa.rasc.ca. And if you want to reach out to me directly as well, president@ottawa.rasc.ca. So thank you folks for coming out tonight. It's a shorter meeting. That means you have a greater opportunity to go out and check the skies tonight. And clear skies. We'll see you in 2 months, and Oscar will see you next month. Thank you for coming out, folks.